5.9 or 6 Kelvin, that is not really meaningfully possible. Just very tiny amounts of heat dissipation that we need to have in the detectors, and attempts at passive cooling would just take it over the edge. And therefore, we need to do active cooling.
So, Constantine, just to clarify, the passive cooling is very similar to what you were talking about with the sunshade earlier when we looked at that first image, right?
That is correct. Yes. So you put the sunshade to block yourself from the sun, and then you put something that's painted black, dark, that does really good job of emitting in the infrared. You point it to the deep of space, and that's how you get to those temperature of 30 Kelvin. Other missions rely on just that method of cooling. Many missions do, including SphereX that you heard a little bit earlier. But for MIRI, that's not enough. For MIRI, we need to do active cooling. And let me jump into what that is. In order for us to cool MIRI, we use a cryocooler. And cryocooler is a fancy name for a refrigerator that works really, really cold. Cryo stands for cold. Cooler means for cooler. If you, I'll show a picture. Can we go to image 14, please? So what you have here is sort of the heart of the MIRI cryocooler. It's several compressors. What you see there in those cylinders is pistons that move back and forth. And some of them one of them at 30 times a second, another one at 90 times a second, and it compresses gas. And then expands it. So as gas is compressed, it gets heated up. You take away that heat and radiate it away into space. And after that, you expand the gas, and then that cools that gas off a little bit more. And then you repeat that many times a second, and you do that in several stages. You take the first stage, you cool that to something like 150 Kelvin, next stage to 50, next stage to 18. And the final stage, you get to something like 6 Kelvin. It's a little bit more complex than that. And if you want to look for more detail, just use your web browser and search for MIRI cryocooler. You'll find a lot more. But generally, that's what this is. It's the most awesome refrigerator in space. It consumes power. If you're familiar with incandescent light bulbs, we used to have those. It uses the roughly light of power of 2 light bulbs. It's just over 100 watts, and it achieves the temperature of 6 Kelvin.
Constantine, this is the most awesome cooler in space, that is for sure. But how does something like this get designed and built?
Well, that's an enormously complex process and long process, and something that involved a very large number of folks. The concept for this cryocooler predated GLBST concept and has been in development for a while. It's a team effort. The cryocooler was developed at Northrop Grumman. The effort is led by JPL. What is happening is that we start with the design. We demonstrate that the design works on the prototype. Then we start designing flight hardware, and then piece by piece build it up, and then test it thoroughly. We go through environmental testing, which means that we expose the hardware that we build to equivalents of rocket launch and the deep of space for thermal reasons. It's a rigorous rigorous process that's common to many NASA missions, and cryocooler had to experience that.
So, Constantine, why don't you tell us a little bit more about the development? And let's pull up image 15. And can you tell us what you see on that image?
Right. So this is the last stage. This is the heat. This is the cold head assembly. This is something that is mounted right next to the instrument, to the optical bench of MIRI. You saw that detector. So that detector would be within a couple of feet from this coffee can. Um, uh, this portion of the cryocooler is right next to the instrument, which also means that it's if you remember the from image of GLBST. Let's actually go to image 2 for a sec. You can see here the primary mirror. What we are talking about is what's behind the primary mirror. What's happening really for GLBST is light bounces off of the primary, hits the secondary. That's the thing that is sticking out, supported by those three struts, and then hits a tertiary that is in that